Here's our second example. We have this toy car backed up against a spring on a hill, so we've got to choose our system. So let's choose the system of the spring, car, and the earth. So looking at that as our system, what kind of energy do we have initially? Well, you can see that, remember I said that you can pick whatever height is 0. So instead of this being a height of 0, it's marked down that this is a height of 0, trying to say that the car basically is not off the ground. It's at a beginning height that's equal to 0. And if that's true, there's no gravitational potential energy. There's a spring obviously in there that's compressed, which means we have some elastic energy. I'm going to this time choose 4 bars. Why did I choose 4? Why not? Right? I get to choose how much energy I start with because it's qualitative, not quantitative. So I've got 4 bars of elastic energy. It's not moving, so there's no kinetic energy. In our situation B, right, and so I had 4 bars of energy over here. So I need to make sure that I have 4 bars total of energy over here to show that energy is conserved. So the spring is released, so there's no more elastic energy. Because it's a car going on a hill, there's something that was deformed, there's probably some dissipated energy. We really have no way of knowing how much, so I'm going to pick 1 bar of dissipated energy. Now notice that the car is higher than where it started. That means that there's some gravitational potential energy. Again, it's qualitative, so we don't know how much. I'm going to go ahead and pick 2 bars. Just seems like a nice number to pick. And then I've got 1 bar of energy left, and that's going to go into our kinetic energy. Because this car is moving, motion means it has kinetic energy, and because I need those 4 total bars, I've got 4 bars now over here on my position B side. For my conservation of energy statement, everything over on the left side, or initially, you list first. So elastic energy, remember, could also be listed as US. That's how it's listed on the formula sheet. Because we've got this dissipated energy over there, that means there was negative work done by friction. And then it's going to equal everything over on position B. So what do we have over on position B? We have our kinetic energy, right? That's how it's listed on the formula sheet with that capital K. And we have some gravitational potential energy, which on the formula sheet is listed as UG. And that would be it. That would be our system. That would be our conservation of energy equation. Now, you're going to see that things are going to change a little bit from question to question, and you're going to have different systems. So let's say I go and I say that, hey, the spring is no longer in my system. So over here in position A, what happens? If the spring no longer is in my system and I'm only representing the energy that my system has, that means that over here, initially, there's nothing. There's no energy of any kind that's stored in the car and the earth. So if that's true, then over here on the B side, well, the car has the kinetic energy, and the car has the gravitational potential energy, and the car has dissipated some energy. So all of that stays the same over on position B. So how did the car get energy? Well, remember, work is how energy is transferred. So because I left spring out of the system, what I need to do is energy is entering my system, and then I need to represent how much energy has gone into my system. Well, there was 4 bars of energy that went into my system. So now my new statement is, my new conservation of energy statement is not US, because that's the energy stored in the spring. Because the spring was doing work on my system, I would have positive work done by the spring, and this would be like the negative work done by friction. So you see how changing your system can change how your diagrams look. Let's change it to one other scenario. I'm going to erase all this here real quick. Now, let's say instead our system now is only the spring. Well, if that's true, initially the spring had all this stored energy in it because it was deformed, but afterwards, over here in part B, the spring doesn't have any energy, right? It's back to its original shape. So where did all that energy go? Well, the spring did work on the car. Well, now, because our system is the spring, it's leaving our system, so our arrow is exiting our circle, because our circle represents our system. And how much energy left? 4 bars of energy left, and it went to the car. Right, so the arrow out is showing that work was done on something outside of your system, so the energy left your system. We're going to do one more just real quick here. Let's go back to our original system of the spring, the earth, and the car. But now let's say that this was our initial height of 0. If that was our initial height of 0, that means that the car had some gravitational potential energy to start with, and the spring was still compressed, right? But it's not moving, so there's still no kinetic energy. So on the other side, it's now moving, so we've got some kinetic, we've got some kinetic energy. It's off the ground, so we have some gravitational potential energy, and it's still, there's some friction, so we've got some dissipated energy. So because we changed where our height of 0 is, we had to add that initial gravitational potential energy. So our equation would be UG plus US, right, for our elastic energy. Energy was dissipated, so that's the negative work done by friction. And then everything over there in position B, it's moving, so there's kinetic, and it is above the height of 0, so there's gravitational potential energy. Hopefully those two examples will help you out and make these bar graphs a little bit easier.